Welcome back, guys. So in point 6, we're going to review our exponential function. So an exponential function is a function represented by a constant base, so in this case 2e and 3, and with a variable exponent. So x squared minus 5 is the exponent. For example, those three. These basic properties of exponents are used when working with exponential functions. So let's keep in mind, these are things that you learned, I want to say it was secondary 1 and or eighth grade seems about right. And then you should have covered it again in secondary 2. So anything to the 0 is always 1. When you multiply two bases that are the same, you can add their exponents to combine them. When you divide two bases of the same, you can subtract the exponents. An exponent to an exponent is multiplication. An exponent on the outside can be brought in by having it to both bases. This is also with division. If it's on the outside, again, you can put it with both numerator and denominator. And one other thing is, if you have a negative exponent, that is like, if you want to make it positive, you need to put it in the denominator, okay? So one thing you need to remember is when we have a symbol other than multiplication and division, you cannot separate or bring them together. Okay, so adding and subtracting don't count. This cannot happen. So let's go over some examples, all right? So first of all, we want to point out that simplified answers are not left with negative exponents, okay? So what we're going to do is break this down without a calculator, okay? So first of all, what I might do is change this to radical form. Remember, the denominator is the radical. So I will say that this is the cube root of 27 to the 4th. Now, the great thing about radicals is that even though I put that under the radical, it's the same thing as saying this cube root of 27 and then the 4th on the outside, because I can, put that in and out. It's all multiplication there. The cube root of 27 is 3. So we have 3 to the 4th, and 3 to the 4th is 81. Okay, so that's what we're going to do with simplifying. All right, well, first of all, 2. This looks a little complicated, but look at that exponent. It's to the 0, so automatically that answer is 1. Okay, there's a couple ways we could do this. We could simplify the inside and then do the square. You can do the square first and then simplify. That is going to be up to you. What I am going to do is do the numerator first. So it's multiplication. I have 5 plus negative 3, which is e squared, all over e to the 4th. And all of this is squared still. Then division, I have a subtraction, right? So we get 1 over e to the 2nd squared. Okay, the larger is in the denominator, so it's going to end up in the denominator. And then 1 squared is 1, and e squared squared is e to the 4th. So there is our answer. Okay. Now in number 4 here, what you might want to do is change the base, right? We can't automatically multiply that because they need the same base. And if you look, we could get 25 to be the base of 5. So I'm going to keep 5 cubed, but I'm going to change 25 into 5 squared. But we already have a negative 2 as an exponent. Now that they have the same base, I can put this together. So I'm going to multiply my exponents first. 5 cubed times, and then this would be 5 to the negative fourth. Now I have multiplication, so I add the exponents. I have 5 to the negative 1. Don't forget, negative exponents is not simplified, so I have to bring that in the denominator, so I have 1 over 5. You can put 5 to the first if you want, but you do not have to. Okay, here we're going to solve 9 to the x equals 27 without using a calculator. Well, the thing is, 9 times itself so many times will not give you 27. So what you do have to do is change both bases. What do they both have in common? They have 3. So I can change the 9 to the x to 3 squared to the x, and 27 is 3 to the third. Okay, I'm going to rewrite that so that I don't have the parentheses there. So I have 3 to the 2x equals 3 to the third. Now, because they have the same base, I can just focus on the exponents. So 2x must equal 3. So x equals 3 halves. Okay, and those are little tricks. Hopefully this sounds familiar. Okay, number 6 here, we're going to use the calculator to graph these functions. Now, what I want you probably to do is use colors so you can see the difference between all 3 of them, okay? So I'm going to do y equals 2 to the x in orange here. So from y equals 2 to the x, don't forget to get into the exponent, you use your caret button right there, that arrow. All right, so graph. Now, one thing that happens here, and you can check in the table, is that at 0, it's 1. At 1, it's 2. At 2, it's 4. Okay, so because it's your factors of 2, so it keeps going up. Now, the other thing is, keep in mind that when you come down here, it does not touch 0. It's an asymptote, okay? So right here, there's an asymptote. Let's keep that in mind. Let's see if I can color that out so you guys can see it. It will not cross, because to have an to do an exponential function, you can never get to 0. Think about exponents as in like 2. So we go 2, 4, 8, 16, 32. If we were to go backwards, what do we get? We go 2, 1, 1/2, 1/4, 1/8, 1/16. But we get very, very small, close to 0, but we would never hit 0 because we're dividing in that case by going backwards by 2. You can keep dividing by 2 and you will never reach 0. So that's why there's an asymptote. Okay, let's do y equals 5x. So, I mean, really, we can use, oh, of course, I did not put on my light. So hold on, let me pause this. Sorry, guys. It stayed dark this time because it is 6:15 in the morning and I'm doing math. Yes, I'm crazy. Okay, so when it comes to y equals 5 to the x, I actually don't need my calculator for this. You guys can try it and make sure on your calculator. But at 0, it is still 1. At 1, it is 5. At 2, it would be at 25. So it goes up quicker, which also means it gets closer to 0 quicker. Okay. And now the one you definitely want to use your calculator for is y equals e to the x. So you can see that. So let's bring that in. Y equals e. By the way, e is in the blue spot right there. Oh, it's where log is, or ln is. It's right here. It's in the blue. So I'm going to go second ln to and the x graph. As you can see, it's the same shape, but if you really want to double check on the values, you will see it still crosses at 0, 1, but here we're going to estimate. So at 1, it's about 2.7, at 2, 7.4, so somewhere up here. So E starts to go in between here. E is a natural value that happens in life. Okay. Now, here are some things at the bottom. Let me put an arrow on that explain to us about the exponential functions and everything. First of all, the base is greater than 1. Okay, so if the base is greater than 1, we have a domain of negative infinity to infinity, right? All the way left, all the way right. But the range is from 0 to infinity. We did not include 0 because we have the parentheses there, so that works. Number 2 here, the graph is continuous. So, and think of it, it's always increasing, concave up, and it has a inverse, right? Because it goes through the horizontal line test. There is a horizontal asymptote at the x-axis, okay? This is actually really nice. We're going to learn this next chapter. It's the limit. So in other words, it's saying as we approach a side, where are we going? So think of it almost like end behavior in this case. So as we go to negative infinity, we're getting closer and closer and closer to 0. So that's why it equals 0. And then as we go to infinity, we get to infinity, right? So we're used to this notation for end behavior, but we're also going to use it for other parts of the graph this year, and we'll learn more about that next chapter. And then, of course, as we can see, the y-intercept is always 0, 1, and that's because we're not adding anything at the end of it, adding or subtracting. And that 1 is comma the base. So like here at 2 to the x, we had 1, 2, and then 4, 5, we had 1, 5. Okay, so those are a little bit of some explanations there. Okay, just 2 more examples, and then you have some time to practice. So the letter E is used as a base in examples 2, 3, and 6, and is not an unknown. Okay, so E is an actual value, is what they're trying to say. Looks like a variable, but it's a value. It is a number called the natural base for exponential functions. It is the most common base in calculus because functions with the base E are easier to differentiate and integrate than functions with other bases. By definition, if we were approaching 0 and we went out 3 decimal places, E is approximately 2.718. Now remember, E itself is E to the first, and that's why we did 2.7 for that coordinate. Okay, and when it says differentiate, you'll get that again very soon, what that means. And there's different formulas to help us differentiate, and the easiest is with base E. When we have other bases, it's a little bit more difficult to remember exactly what to do. Okay, so with that, we're going to sketch without a calculator. Okay, so of course, what is the first point? We know the first point is 0, 1, and we know at 1 it's going to be that 2.78. So that's good for you to memorize, guys. This 2.7818, so that way we know the value it is really close to. And we know it goes up to infinity, and we know it comes down at the asymptote of 0. Okay? Now, using the adjustments to the graph from example 7, graph f of x of e to the negative x plus 1. Okay, first of all, let's talk about what's going on right here. So when we shift, let's actually talk about the asymptote first. Okay, this shift here, plus 1, goes up 1, right? So that asymptote, even if on the inside here, I should do that another color, because this is to x. This is not the negative on the outside. This is negative on the inside. So that means we're going to reflect across the y-axis. If it was on the outside, guys, it would be in front of the e. So first of all, as you can see, if we move the asymptote up and reflect, it's a horizontal line anyways. So I can do the asymptote at 1 right now. Okay, now that also means that the y-intercept went up by 1. So I know instead of 0, 1, it's 0, 2. So I can plug that in. Now, the thing is, before we had 1 and 2.718, but if we're reflecting it, that means it's going to be at negative 1, 2.718. So at negative 1, 2.718, and then I know that it will incorrect, Jennifer, sorry, because we moved it up, didn't we? So it's not at 2.718, it's at 3.718. Okay, do you guys see my mistake there? Because I forgot to move that point up too. There we go. And then we come across the asymptote. So remember, because we're going up 1, instead of it being at 1, 2.718, because that was the original, right? So if we move it up 1, it's going to be at 3.718. And when we reflect it over the y-axis, it becomes negative 1, 3.718. I hope that makes sense now that I'm changing that coordinate. So this is the one that we want on the new graph. All right, so practice your review on exponents and see how we do.